In this video, I'm going to walk you through Lesson 7 of Unit 8.1 from Open SciEd. All right, we just started the next lesson set where we're going to start really thinking about energy and how energy is connected to force interactions. We started talking about it at the end of Lesson 6, at the end of our transfer task. And so now we're wondering what does happen when we double the mass or double the speed? How does that affect the damage that happens from this force interaction? So first we're going to plan an investigation and we're going to introduce the materials that they're going to use. Let me open up this slide that you will use. And you'll see that we have a cart system again. And this time we're going to use that push-pull spring scale to actually measure the amount of force we're putting into the system. So you're going to pull that cart back against the plunger. The plunger is going to come back a certain amount of newtons. I think at the first time, I think it's 5 newtons. You pull it back, and when you release it, the cart's going to be pushed forward from that plunger with a certain amount of force. We're going to begin by calculating the speed at that level of force to get our original baseline speed from pulling it back of 5 newtons. You'll look in the procedures because the newtons change in different setups. Here we have a saltine cracker that is taped, or actually that's a little bit of sticky tack that is on an index card. They're going to put their names on the index card and which condition this is. We've got 3 conditions we're testing, condition A, B, and C. And so they're going to basically move this cart at a certain speed with a certain amount of mass into this cracker, and then some damage is going to occur. After investigation 1, we're going to compare, maybe do a gallery walk of all the damage so we can see which one has more damage. Was it doubling mass or was it doubling speed? And I will say this paper collects the crumbs, but this is a very messy investigation. So I have heard of teachers putting this index card with this saltine cracker in a sandwich bag, in a Ziploc bag. So you collect the mess and you just compare the Ziploc bags rather than comparing all the crumbs on a piece of paper. Just a little tip to avoid the mess. Okay, so then we're going to discuss an approach to investigating more than one variable at a time, because up until this point, we've been really clear on we're only going to have one independent variable that we test at a time. But we want to look at doubling the speed and doubling the mass. So how do we do that? So here's a little discussion that will happen around 3 different conditions. This is found in the teacher guidance. And so you will see that we have 3 conditions. The first one is going to be our original mass, so the mass of the cart, the way it is, and the original speed. So if you pull back 5 newtons, what's that speed? How far did it travel? How fast did it get there? We're going to then calculate the speed for our original numbers. For condition B, we're going to double the mass. So you're going to add stuff onto that cart like washers and paper clips to double the mass, but we're going to keep that original speed. Now, because there's more mass, you got to pull it back a little bit more. Read the procedures. I think it goes to 7 newtons to make the speed be the same as the original. But I would have them time it and see how far it goes to make sure, or you can actually do this before, make sure your system actually doubles the speed by pulling it back a little bit further. Condition C, you will see we have the original mass. So you're going to take those extra washers and paper clips off, but you're going to double the speed. Now, the way the procedures are written, you're going to pull it back. I think it's 10 newtons. So just read the procedures. I would test this before you do it to make sure your system doubles the speed with being pulled back an extra so many newtons. So then we're going to carry out investigation number 1. Students are going to do this in their lab groups, and they're going to record the data on a handout. You can see the handout looks like this. So you can see we're going to have the original mass in condition A. We're going to double the mass in condition B and then go back to the original mass in condition C. For the length of the track, that's going to remain the same. The time it's to reach the end is going to be needs to be very similar in these 2 to create the same speed, but we are going to have half the time to reach the end because we're going to double the speed. And so when you pull it back, it should go faster to reach the end of the track. And so this is all investigation 1, and we're going to compare the damage. And investigation 2 you will see we're going to be looking at the same three conditions, but we're going to be using some videos, and we're going to record the data from the videos. So here are the three videos we're looking at. Each one has the same system, but we double the mass and we double the speed in conditions 2 and 3, or video 2 and 3. You will see that we have a cart. We're going to use the same plunger system to make it move, but there's a box on the track. And what we're going to do is quantify the distance that box travels, because the box starts at the beginning of the meter stick and then it gets pushed to here. So here is the distance that it traveled. Well, when you double the speed, it's going to travel further. When you double the mass, it's going to travel further as well. So now we're first we looked at damage. Now we're looking at quantitative data of how far the box moves. So the box moving is representing the amount of kinetic energy that's being transferred from the cart to the box. Now, if you struggle to get the data from the videos, there is sample data right here that you can use. It comes from the teacher edition. So after we collect the data from the videos, we're going to compare and discuss the distances traveled in each scenario, under each condition. And so we talk about how many times further did the box go when it was pushed with double the speed? How many times further did the box get pushed when it was doubled with the mass? And really what we're starting to develop here is that there is a relative increase in the distance the box is pushed as a measure of the relative increase in the kinetic energy. So the more the box is pushed means it has more kinetic energy. We are then going to prepare for investigation 3, and investigation 3 uses a computational model, a simulation. And so we're going to set up our notebooks for some data tables. You can create one for your students if it's easier, maybe even put it on your other data sheet. But the point is that we're going to use the simulation. Let me open it up for you. So you can see that you're going to click setup and the cart and the box will appear on the track. When I hit go, the cart moves and it pushes the box. So it's the same thing we're watching the videos, but now it's a computational model because we have numbers we can use. So distance the box was pushed. Here's our initial speed. Here's our initial mass. So I'm going to actually increase and double the speed. I'm going to hit setup again and it's going to go. So we can use these numbers. These are the numbers they're going to put in their data table. So once we're done with the simulation, we're going to graph our results. And so here is some graph paper that you will use. I will tell you that there is an alternate version that already has the Y and X axes labeled, probably a little bit easier to use with your students, depends on their familiarity with graphs. And we're going to analyze and interpret our results. And what we're going to find is that there are some relationships here. So we're going to look for patterns in our graphs. How many times, if you had 3 times as much mass, but the same speed, how much more kinetic energy would there be? So we're going through these questions that are provided on a slide for you. And what we're trying to figure out, and we're going to document this on a class chart, is that for changes in mass, there's a linear direct proportional relationship. So however many times more mass there is, there's a linear direct relationship to the amount of kinetic energy. So if I double the mass, I'm going to double the kinetic energy. So for changes in speed, however many more times there is speed, it's actually squared. When you double the speed, it's going to quadruple the energy. And so this should also relate to the amount of damage we saw, because when there was double the speed, we saw a lot more damage on the crackers. So we connect back to our anchoring phenomenon and we talk about kinetic energy changes in a system. And there's a handout that they're going to fill out. There's some questions that they're going to answer. And then we're going to look back to the interactions in systems poster that we created in lesson 2. And so we're talking about when you've got one thing that was moving and the other thing wasn't. We're going to start really building that idea of energy being transferred and what's the effect of that. And so the kinetic energy is going to change in both. This has a lot of kinetic energy, but then it transfers some to the non-moving object. And so both of the objects have a change in kinetic energy. Object 1 is a reduction. Object 2, it's going to increase. But force, we're still a little unsure about. We need to do a little bit more investigating about the force in the system. However, what we're problematizing here is that where is the energy coming from to go into the system and where is it going? Because we know that energy is neither created nor destroyed. We actually did this in some other units. And so where's it going? Where's it coming from? That's where we're going to go in lesson 8.